Begin the course with a bit of a review of the important functions that we will be using throughout. This includes some pre-calculus and some Calculus 1 material review, and if you require a more in-depth look at these prerequisite function knowledge, then please take a look at the pre-calculus refresher modules that are posted under the course materials tab in our Blackboard shell. Well, let's recall that calculus is a study of change. And the dynamics of change most noticeably occur through time. These are the pictures of my daughter as she was growing and continues to grow. And some of you must have seen these pictures before if you have taken Math 111 with me last semester. When she was still inside of me with the ultrasound, it was the femur length that her growth was determined by or tracked by. When she was already a baby, it was the height the doctors were measuring, and now that she's a toddler, it's the weight they're tracking. The important thing is that each one of these is a function of the corresponding variable. So for example, the femur length is a function of time in weeks of the fetus growth. The height of a toddler is a function of time as they are after they're born. And finally, the weight of a slightly more older child is a function of their height, which makes a little bit more sense. Babies grow more or less uniformly in weight and height, whereas later on in life, genetics kick in. And for example, my child is never going to be very tall because I am not. Now, this means that it's these types of functions that we will be, of course, interested in, as well as many others. The easiest one of these is this function for the height, and this is what is known as the linear function. This next function here is a bit more complicated. It is known as a polynomial. And finally, this weight function has a non-integer degree, which means that this is something that we will call power functions or exponential functions. Let's take a look at how the linear and power functions in general actually work. The linear models are the easiest models and often will form the basis or the first step of developing a model. These are the very familiar equations of lines, hence the word linear. The graph of a linear function is always a line, and when written in this particular shape, we recognize the m as the slope and b as the y-intercept. So if I draw a general line here, I can immediately, on the sketch, recognize this as the y-intercept b, and then the other characteristic of the line is going to be the slope, which is the rise over the run. Now, of course, in Calculus 1, we've also seen the slope being defined as the derivative of the function, and this is the connection that we will be making throughout. So this is rise over run, or the rate of change, or the derivative. This goes by many names. Now, let's take a look at one particular example utilizing the function from the previous slide. So this function has been derived with the US collected data on a lot of samples of the heights of girls of age in months that is given by this function in inches. This is, of course, the average height of a girl. So if you plug it in and it doesn't quite match what you or your child's height is like, that's because it's not supposed to represent every possible human's potential height. So the first part here is asking to calculate the average height in 10 years. In word problems, you always have to be careful about units. The function is given to us to be computed in months, and we are asked to compute something in 10 years. So first of all, we have to make sure that our units match. 10 years is the same as 120 months, which means that in order to calculate the average height, I'm going to have to replace this t here with 124 months. And then my result, once I actually calculate it, turns out to be 54.2. The units of the height here are given in inches. As I mentioned, this is the US collected data, so the units are imperial here. The second question is asking how fast is the height changing at the age of 10 years. So not what the height is, but how fast is it changing? These are the keywords here that you should recognize from your Calculus 1 experience as something that connects the actual function with its derivative. The derivative measures the rate of change. How fast means we're interested in the rate of change, and the rate of change of a function is its derivative. So what we're going to do here is take our function h of t and take a derivative of it. Now, again, this is changing with respect to time as the child grows, so I'm going to be taking the derivative with respect to time. Let's recall here two different ways to represent the derivative in terms of just notation. There is the prime notation, and then there's another notation that sometimes can be useful in word problems, what we call a Leibniz notation, the one that actually makes the rise over run look consistent with its notation. It's going to be dh by dt. This notation is good because it helps us track the units, because it makes it very clear what the units of the top and the units of the bottom are, and then the overall units of the derivative will be the ratio of the two. So if we want to take the derivative of this with respect to time, let's remember our differentiation rules. The constant here will simply go away, so this will turn into 0, and then the derivative of 0.185t is going to be just 0.185. Now it comes with units, so again, taking a look at this notation is probably going to make it easier to come up with units. The units for h, which are the units of the top here, were inches, and the units of the time, which are on the bottom here, were in months. So overall, I have inches per month. So we notice that the rate of change here is a constant. So when I want to plug in 10 years or 120 months from the birth of the child, I'm going to get the same exact number of 0.185 inches per month. Now this is one of the defining properties of a line. No matter what 2 points I pick on the line, the slope or the rise over run is going to be exactly the same. Whether I pick these 2 points or I pick these 2 points, the values for the rise and run will change, but their ratio or the slope will remain the same. So this means that as far as this function is concerned, the rate of change is constant for the entire time of the growth, which of course begs the question, is this model good for long-term growth? If it's constantly increasing at the rate of 0.185 inches per month, can we say that this is something that we can track a female height at for, let's say, 90 years? Well, of course not, right? This is not something that will hold for a very long time. And in fact, what is missing here is the domain of when this model is going to be reasonable and appropriate, which is up to 12 years. So 10 fits within the model's reasonable domain, and otherwise, this becomes a little unrealistic. This is true of many linear models. They are very good at modeling something on a short term, but not very good for something on the long term, which begs the question of what other models are there? The next step up are going to be power functions. Power functions are functions of this form, kx to power n, where k and n are various constants, and we actually will assume that for now n is an integer and is a positive one at that. So we're not going to be looking at the reciprocal functions just yet. Just to get a feel of what these functions might possibly look like, we will take a look at two cases here. First of all, we're going to fix the k, and we will let it be 1. So I'm going to basically ignore the fact that k is there, it's equal to 1, and I'm going to vary this value for n. So what we're going to get is things like x squared, x cubed, x to the fourth, and so on. What do these functions look like? Let's do a quick sketch of what we think x squared, x cubed, x to the fourth, and so on look like, and more importantly, what do they look like together on the same graph? So of course I know that x squared is just a parabola-looking function. I can sketch a rough graph of it here. There you go, something along these lines. I'm sketching by hand, right? So please keep in mind that if you're using a software to do this, which I will do in a minute, your graphs are going to come out to be a little bit more precise and prettier. Once I have x squared and I would like to graph an x cubed, I have to ask myself a couple of questions. If I were to just graph x cubed on its own, I know that it's a snaky-like shape like this, but now that I have x squared here, I have to think about how these two functions will interact. And this is something that we've talked quite a bit about in our Math 111 class, so this should be a refresher for those of you who have seen it before in there. If you plug in various numbers, so for example, if you plug in 1/2 into x squared and then 1/2 into x cubed, you will notice that for smaller powers, they will be higher numbers, higher outputs near the origin. So near the origin, x cubed is going to be flatter, but then at some point it will surpass x squared and will start growing faster, because plugging in larger values into larger powers will result in larger output. And then for x to the fourth, the same pattern will hold, but you gotta keep in mind that x to the fourth, the even power, will once again keep a parabola-like shape. So what I'm going to have is a function that should look like a parabola, but keeping in mind that near the origin, it's going to be flatter still, and then it's going to surpass both of these functions in order to start growing even faster, okay? And let's pretend that this is symmetric with respect to the y-axis. So generally, what we have for our functions is that if the power is even, we're going to get a parabola-like shape, even power, and if the power is odd, we're going to get a snaky-like shape, okay? And then the other properties to notice are how these functions look like near the origin. The higher the power, the flatter the function, and then away from the origin, the higher the power, the taller or the faster the function grows. On the other hand, we can fix the power. So let's say we fix the power to be square, so we will be looking at parabolas, but vary the coefficient in front of it. So for example, here, notice that I have x squares all over the place, but then I have x squared and then double that, 5 times that, minus 3 times that. What would that mean for how the functions interact with each other? So again, let's make a quick sketch by hand here to see how this might look. I will start with the basic x squared, the basic parabola, and this is something that should be familiar from the pre-calculus and the various studies of function transformations. This is x squared, my sort of base case. 2x squared means that my function has been stretched out by the factor of 2. So what we will see is a taller, skinnier version of the exact same function. So this is 2x squared. The higher the coefficient, if it's positive, the more stretched out vertically the function will be. So 5x squared will look something like this. Now notice that I'm not putting any scales on my axes, meaning that I'm really only looking for this sort of qualitative feel of what these functions look like with respect to each other. If the coefficient is negative, that means that I'm also looking at the flip in with respect to the x-axis. And also remember that sometimes if the coefficient is negative, that means the parabola is looking down, so that's another way to think about this. If it's minus 3, and this was my original x squared, I'm looking at something that's a little bit more stretched out than 2x squared, so if I'm going to make a reasonable sketch, then it's a function that should probably look something along these lines, minus 3x squared. Now, drawing by hand is a very handy tool to visualize these functions, but of course, being in front of computers, we have all kinds of possible technology to aid us in visualizing these functions. Desmos is a free online graphing calculator. So you just type in desmos.com, go to the graphing calculator, and it has a very intuitive way to actually type things in. So I'm going to type in exactly what we've had on the slide, which is kx to power n. And what the software does immediately is it actually offers me to add sliders. Sliders for everything that's not x, so for everything that is not a variable. So I clicked all, and there we go. I can play around with the various values for k and the various values for n. I am only interested in positive powers, positive values for n. And in fact, I'm only interested in anything above 1. So let me say I actually want to go between 1 and let's say 6 with a step of 1. Okay, so you can fix all kinds of things you want here. In our first example on the slides, we actually allowed k to be just 1 and then varied the values for n. So let's see how that will work out. You can slide the slider across. There's our parabola. There's our x cubed, there's our x to the 4th, and so on. Or you can actually hit the little play button and it will move the slider for you back and forth just to see a little animation of what happens there. What we did next was to fix n at 2 and then play with the values of k. This is probably where the play button actually makes a little bit more sense. You can see as the k increases and becomes negative, that the function goes from a wide parabola to the long stretched out version and then pointing downwards. Now, if you do want to see the various functions on the same sketch, you will have to type them in separately. So for example, if we wanted to see x squared versus x cubed versus x to power 4th versus let's say x to power 5th, we would have to sketch them all separately, but then I can also zoom in on the graph. I'm on a tablet, so I can do it with my fingers, or you can do so with the plus and minus button on the side here, and we will witness that exact same pattern that we've seen on discussion on the slide, is that the higher the power, notice that as I go from x squared to x cubed, to x to the 4th and so on, I get the function to be flatter and flatter and flatter near the origin, and then there is a switch point here at 1, after which the behavior completely changes to be the exact way, the exact opposite way. And this is something that we're going to discuss next. Power domination is an extremely handy tool for discussing power functions and then by extension polynomials, rational functions, and so on. So this is something that we're going to be using throughout. What we have on this graph are the functions x squared, x cubed, x to the 4th, and x to the 5th. Just based on the logic from the previous slide that talked about the general shape of even and odd powers, we can already notice that what we have on this side here will represent x to the even powers, these two guys, whereas if they're going to follow the snaky shape, these are going to be x to the odd powers. That narrows it down somewhat, but if we have to label each function as exactly one of these, we're going to have to think a little bit further. What the power domination suggests is that you notice that here, near the origin, the red function was the highest. It had, for the x value, the highest y value, whereas after the switch point at 1, it became the lowest, the one that produces the smallest y value for any given x value here. So in the power domination, what we say is that near the origin, small powers dominate, whereas from the switch point on, large powers begin to dominate. Near the origin, the function that comes out on top, dominate meaning produces the highest y value, is the function with the smallest power overall. After the switch point, the function that comes out on top with the highest y value, the one that dominates, is the one with the largest power. And that is fairly easy to check with just plugging in various numbers. Let's say if I compute 1/2 to power 2, 1/2 to power 3, 1/2 to power 4, for example, I notice that 1/2 to power 2 is 1/4. Then I get 1/8, 1/16. And let's say I compute all the way down actually to 1/5, 1/32. So what I notice here is that if I plug in a small number, less than 1, into the small power, the output 1/4 is like 0.25. Whereas if the power increases, my output becomes smaller and smaller and smaller. 1/32 is quite a bit smaller than 1/4. Whereas if I plug in values that are above 2, let's say 2 squared, I compute with 2. So this is for 2 cubed is 8, 2 to the 4th is 16, 2 to the 5th is 32. If I plug in large numbers like 2 or 12, 20, and so on, then the output grows as the power itself grows. For small values, the highest number is produced by the smallest power. For large values of input, the highest number is produced by the highest power. And this is what this power domination dictates. The near origin behavior is determined by small powers. The end behavior near the infinities is dictated by the large powers. This makes it very easy to start determining which functions are which if you have more than one drawn on the same graph. So for example, here, I've also added the coefficients, which means that my switch points or intersection points are all over the place, but the power analysis will still hold. Near the origin, the smallest power will be the top one in terms of the y values. So I can see that the highest one near the origin is the red one. It's also the slowest growing one at the end, which means that that corresponds to my x squared function. So this will be my x squared. This will be the same at x squared here. The next one down will be x cubed because it's going to grow a little bit slower near the origin and a little bit faster further away from it. So this will be my x cubed here. And then the highest power overall, the x to the 4th, will be the flattest near the origin and the fastest growing one for large values of x. So this will be my x to the 4th with a coefficient. Now, if we have two particular functions, not only can we determine the overall quantitative behavior, but we can start thinking about putting the actual scales on the axes and finding specific points of intersection. So let's take a look at this one here. We have 3x to the 4th and 5x to the 7th. We're asked to sketch them and then find the points of intersection. I strongly recommend producing a qualitative graph first, so no scales, no nothing. And that is because sometimes you might get lost in the algebra, whereas the qualitative sketch will suggest some general big picture ideas that have to hold through anyways. So let's sketch the 3x to the 4th first. The coefficient is positive, so it's going to be the standard sort of without the reflection function. X to the 4th means that I'm looking at the power function with the even degree, which means that it's going to be a parabola looking one. So overall, I have something that looks like this. Now the next one, 5x to the 7th, means that it's going to be an odd power. 7th is an odd power, which means that it's a snaky looking shape, so it has to look something like this. Now, because I already have another function drawn here, I have to think carefully about the interactions between the two. This first piece I can draw no problem, but then I have to think about how am I going to draw my snake? Is it going to go below the parabola or above it? Remember that near the origin, smaller powers dominate. The smaller the power, the higher it is. The higher the power, the flatter it will be, which means that for my x to the 7th, near the origin, it has to be below x to the 4th, and then eventually it will surpass it and start growing faster and faster. So this already shows me that what I'm expecting are 2 points of intersection, one at the origin and then one somewhere here, the switch point, before which the 7th power was flatter near the origin, and after which it's going to actually surpass the 3x to the 4th. Now let's do this algebraically. Points of intersection is where two functions are actually equal. So I'm going to have 3x to the 4th is equal to 5x to the 7th. I'm going to move everything to the right-hand side here. And then I'm going to be very careful about solving this. Do not divide, factor. I can see that I can factor out x to the 4th, and what I'm going to have left is 5x cubed minus 3. Factoring is a very powerful technique because it gives me two pieces who multiply to give a 0. the only way a product is ever equal to 0 is if one of the pieces is equal to 0. So this immediately gives me either x to the fourth is 0 or 5x cubed minus 3 is 0. And I can solve those two equations separately. X to the fourth equals 0 implies that x is equal to 0. And then, of course, I can see that at my point of intersection right here. And for the second equation, I'm going to have to work a little bit harder at solving it. I can isolate the x. So I'm going to get x cubed is 3/5. And then I can take cube root of both sides to end up with x being equal to cube root of 3/5. Now be careful here. If the power is odd, I'm going to get only one odd root. If the power was even, I would have ended up with a plus minus. So if you want to review your exponentiation rules, please take a look at the pre-calculus refresher modules once again. So the second one corresponds to my second point of intersection of the two graphs right here. Again, drawing a graph before doing any of the algebra established an expectation for 2 points, so in case you accidentally ended up with introducing the plus minus, you would have noticed that it's not quite consistent with your graph. This power-dominating analysis can be extended very easily to functions that are not just powers, but rather polynomial functions, power functions that are connected with pluses or minuses. The polynomial functions, their graphs are always smooth, what we call differentiable curves, so there is no corners or cusps. A derivative exists all over the place. And we can actually use this dominating power analysis to sketch rough qualitative graphs of these guys. So let's say I have this example here of x cubed minus 4x. Remember, from the power analysis, we know that near the origin, small powers dominate. Now my function here consists of two power functions. I have the power function x cubed, and I have the power function minus 4x. Each one is a power function, and then they've actually been added together. So near the origin, small powers dominate, which of course is minus 4x here. So I'm going to note that this dominates for small values of x, or near the origin. For large values of x, I'm going to have that the large power dominates. So this dominates for large values of x. And this alone should give me some idea of what the graph sort of looks like near the origin and at the ends. Right? So what I have here is that near the origin, it looks like minus 4x. Well, I know fairly well what minus 4x looks like. It's a line of slope -4 that goes through the origin. So near the origin, my function should look like this. Again, notice that I'm not actually drawing any scales on just yet. If I want to produce a more detailed sketch, I will, but for now, very qualitative analysis. For large values of x, my function looks like x cubed. So overall, x cubed looks like this, my snaky shape, but here, that shape will only persist for large values of x. So I'm not keeping the entire shape, I'm only keeping the ends of it. The beginning end, then I'm not interested in what happens in the middle, and the last end, only something that holds for large values of x. So I'm keeping the ends of the x cubed as my pieces that my function will actually replicate. Now, even this alone gives me a fairly good idea of what this graph will look like, right? I have to start here, and then I have to somehow get to this piece and connect on the end there. So it seems that if I am to produce a nice smooth curve, the only way to go about it is to connect the pieces this way. Now I notice that this introduces potential intersection of the x-axis, so if I want to produce a more accurate sketch, I can even think about computing the intercepts here. Let's take a look and see if the intercepts computations will support my expectations for what the graph should look like. So let's start with the x-intercepts. For x-intercepts, we're going to set y to be 0, which means I'm looking at solving the equation x cubed minus 4x is equal to 0. Again, don't cancel, factor. If you cancel, you might actually lose a root. So I can factor out one of the x's, and then I'm going to have x squared minus 4 left in the bracket. Once again, Factoring is useful because it means that I have a product. A product is ever 0 if one of the pieces is 0. So that gives me either x is 0 or x squared minus 4 is 0. Well, x is 0 is already a solved equation, but x squared minus 4 can be turned into x squared equals to 4, which means that x is equal to plus or minus 2. So this is all of my x-intercepts. I have that the function intersects the x-axis at 0, it intersects it at -2, and it intersects it at 2. This is where it's important to remember that even functions will produce two roots. If I wanted to compute the y-intercept, or y-intercept, it will always be unique if it exists. I'm going to set x to be 0, and what am I going to get? 0 cubed minus 4 times 0 is 0, so my y-intercept is the same as my x-intercept, which is at the origin. Okay, so now with this in mind, I have to make up a function that looks like this on the ends, looks like this near the origin, and goes through these 2 points. At this point, I really have no other choice but to have a function that goes through -2, turns around, produces a linear behavior near the origin, and then connects to my end over there, right? So once again, thinking about the power analysis beforehand will set up an expectation for what the function looks like. And if you made a small mistake in your arithmetic here and accidentally only ended up with +2, which is a mistake I see often, this wouldn't quite work out with your power analysis, and you would know to look for the mistake in your calculations.